Hello, so today we are going to do this problem, which is part of Leetcode daily challenge, minimize maximum of array. So we get an array of numbers that has n non-negative integers, so positive, and we have one operation we can do where we choose an integer I in the array such that the number in that position is bigger than 0, and we want to decrease that number by 1, and we have to increase the previous number by 1. So we can choose an index, and the operation is to increase that number by 1, but to decrease the number, by 1, but that has to be paired with increasing the one in the previous position by 1. And the goal of the problem is to return the minimum possible value of the maximum integer of numbers after performing any number of these operations. So the minimum possible value we can make of the maximum number after performing number of operations, right? So of all the arrays we can do with any number of operations, which one minimizes the maximum of that array? I hope that makes sense. So that's sort of the problem statement. If we take a look at this first example, what can we do? So we can, in one operation, we can choose index I equal to 1, which means we will decrement this number and increment the previous one. So that would be 4, 6. And then the second operation, we can choose I equal to 3, so this one, which means decrementing this one and incrementing this one. So that would mean making this 5 and this 2. Okay. And then the second one we can make is choosing I equal to 1 again and decrementing this and incrementing this. So we'll get 5, 5. That will give us this. Okay. So that's the idea. And so we can't do better than this, because if we try to decrement any other number, then we'll end up incrementing 2 more the other number. So what I mean by that is, if we choose this one and we try to decrement it, then we'll get 4 here, but we'll increase this, making this 6. So the maximum is actually bigger than 5. If we choose to decrement 2, there is no reason to decrement it, right? Because it's already smaller. If we choose to decrement this 4, then we will still have these numbers as higher, so the maximum will still be 5. So this is basically the best we can do. So we return the maximum of this, which is 5, and that's the minimum possible. So that's the idea of the problem. Now, how do we tackle it? Okay, so how do we tackle this? So let's take a look maybe at one example. So let's say the first one, 3, 7, 1, 6, and think about this. So the problem says we want the minimum possible, right, value of max number in array after any number of operations. Okay, so already you can see the min possible value here. You might think, okay, maybe we can try basically different set of numbers, right? Let's say 1, 2, 3, 4, 5, 6, right? All the way, basically all the possible numbers, right? Or maybe even up to the current max of the array plus 1 or something like that. And just try all of them and see if it's possible to reduce the array, right, such that the maximum is one of these values. So what I mean by that is check, is it possible to, after some number of operations, to make the maximum number in the array 1. And then if the answer is false, try 2. If the answer is false, so sort of a brute force, try all of them, and then the smallest one that achieves this, return that. Okay, so that's definitely an approach. The other thing to think about is we actually don't need the exact number to be the max, right? As long as we check if it will make all the numbers smaller or equal to that value, let's call it x. So we try x here, smaller or equal to 1, right? Because if it's if we can make all the elements smaller or equal to x, then we can increase, we can keep decreasing one of them until the previous number becomes equal to x, right? So basically, checking if we can make one value a max is similar to checking if all the elements in the array, right, are smaller or equal to x. Okay, so that's sort of one observation here. Okay, so that's actually an interesting observation. So trying all of these will be too expensive, right? Because for each one, we'll have to check if all of these are smaller or equal to x, are possible or not, right? So a better one would be to binary search in this range to find the minimum value possible such that we can do this. Okay, and this actually is possible because with binary search, as I usually explain in other problems, I also have a video about this, so you can take a look. What we can do is try to find a function, right, f of x, such that that function starts out as false in the range we are searching in, and then at one point it becomes true. And once it becomes true, the bigger values of x will always be true. So if it's true for 4, that means it will be true for 5, it will be true for 6, all the way up, right? And before that, it may be false for 2, for 3, for 1, but once it becomes true, it stays true. So this is the definition of monotonic, where you can apply binary search. So if we find this, then the last value of high in binary search would be the first true, and the last false would be the value in low variables in binary search. So the first true, we can just return high if we are looking for that. And so for our problem here, how can we make this? How can we find a function like that? Well, actually, that's what I said here, smaller than or equal to x. So we can just find, right, if for a number, right, we can make all the values, right, in numbers smaller than or equal to x using the operations we have. Doesn't matter how many operations, but using any number of operations. Now, if we can find this, right, so that means, does this function apply? So let's say we can make all the numbers in nums smaller or equal to 5, for example. Does this mean that we can make all of them smaller or equal to 6? Is that true? Well, let's take a look. So if we can make all of them equal to 5, since 5 is smaller than or equal to 6, right? By definition, it's true, right? Because if 4 is smaller or equal to 5, well, that means 4 is smaller or equal to 6, right? If any number a is smaller or equal to 5, that means it's smaller or equal to 6. And since this is valid for all numbers, that means this is valid for all numbers as well. And you can apply this by definition to x, and then x plus 1. If it's valid for x, it's valid for x plus 1, for x plus 2, all the way to the end. Okay, so that means we have this pattern. Now what about, so we have this pattern of first false, and then after that it will be true. Now, are there cases where it's even false? Well, yes, because for example, in this case of this array, if we take our x to be equal to 4, we actually can't make this 7 here equal to 4, smaller or equal to 4, because we can subtract 1, and that will make the previous number increment by 1, so we'd have 4, and then we'll have 6 here. But if we try to decrement more to get 5, well, this one will increase. If we decrement more, this one will increase. So if we decrement more, then we'll make this number not smaller or equal to x. But if we don't decrement, then this number would be bigger than x, right? So if we decrement, this one would be bigger than x. If we don't decrement, then this one would be bigger than x. So it's not possible to make both of these smaller or equal to 4, right? And so that's an example where it's false. Okay, so now we know that this applies to binary search. Okay, so the only thing left to do is just specifying what this function is and what's the range. Well, the range is simple. We can just take all the possible numbers, which the problem says the values are between 0 and 10 to the power of 9. And so with this method of binary search, we'll just pick values in the boundaries just before our range here for low. So that would be -1. And just after our range here for high, which would be 10 to the power of 9 plus 1. And just search in this range, right? And we put these values in the boundaries explicitly just to avoid worrying about cases where the entire search space is false or the entire search space is true, right? Because that's a possible case. And so we know the values of low and high. Now how do we calculate this function? Now that's the tricky part. So basically our function that we are looking at, let's call it can x, or we can call it f of x, is can we, using any number of operations, make all numbers smaller or equal to x in the array? Let's pick a couple of examples. So let's say with 3, 7, 1, 6. And let's pick maybe the x here equal to 5. Or actually, let's pick x equal to 4, right? And let's see if that's possible. So let's start out here. Is it possible to make this number is already smaller than x, so we should be good, right? Let's see here. Is it possible to make it equal to 4? Well, no, because we can try to decrement once. So that would be 6 here, 4, 1, 6. If we try to decrement again to 5, then this one would be 5. And so that's not smaller than or equal to 4. Now, how do we do this in a, code it actually properly? So notice here, the answer for this number, so if it's smaller or equal, the answer for this one is good, but the answer for this one depends on the previous number. And in what part it depends on the previous number? Well, it depends on what is left from this number such that you can increment it without violating the condition. Because when you increase I, you have to decrease I minus 1, right? And so basically what we are trying to see is by how much can we, when you decrease here, you increment the other one. So what we are trying to see is by how much can we decrease 7 such that 3 doesn't exceed x. That's what we're trying to do. Now, what's that value? Well, the value is just how much buffer is that you can increase 3 such that it doesn't exceed 4. What's that value? That's just 4 minus 3 equal to 1. Because if you add 1 here, it will be 4. But if you add another one, it will be 5, which is bigger than x. So what is this? This is just the value of x minus the value in I minus 1, the previous position. Okay, let's call this nums in the array. Okay, and so what this means basically is that for each number, we just need to know how much is left out from the previous number that we can use for our number here. So let's apply it then and see what this will look like. Okay. So how do we do that? So let's actually just apply it. So first, we can just go here at this 3 and look at this 3 here and say for the next element, right? Just subtract what's left. So here we have 4 minus 3 that we are allowed to subtract from the next element without this one exceeding the x value, right? So this is 1. So that means we can decrement 7 by 6 without causing this one to be bigger than x, right? And so we just do 6 here and proceed. And here we want to see how much this is bigger than 6 is bigger than x, right? And so we can immediately stop and return false. It's not possible because if we know that but the previous element we can increase it by as much as only 1, right? But even since we took that into account, but still the number is bigger than x, that means it's not possible, right? And so we can return false immediately. Now, what if we had something like Now, so what if we had, let's say maybe 3 and 5, and then maybe, let's say 4, and then 6, and then 1. And then x is still 4. So let's try that. So we try x, so 3 is smaller than x, so we are good. And we want to know how much we have left for this one to use. Because when we subtract from this, we have to increment from the previous one. And so what we have, x minus 3, which is 1. And so we subtract it. Now this is 4. We go here. 4 is smaller or equal to x, so this is valid. And so how much is left? Well, x minus 4 is 0, so nothing is left. So we check here. 4 is smaller or equal to x, so it's valid. How much is left? X minus 4 is 0. And so we check here. 6. Well, 6 is bigger than x, and we have nothing left to use. And so we can just return false. Okay. Now, if we had 3 here, if we had, let's say, actually 2 here, then we will see, okay, what's left? X minus 2, which is 4 minus 2, so it's 2 is left. And so we subtract it from here. Notice, as soon as we find that something is left, we subtract it from I plus 1. So that when we get to I plus 1, we can find that it's within the target. And so when we subtract it, 6 minus 2, that's 4. So that we do that here. Now when we reach I plus 1, 4, we find that it's smaller than, or it's within the x value, so we are good. And we get to 1, it's smaller, we are good. So this array would be true for it. So that's the idea of how we can do our f of x function in O(n) time. Right? Basically, because the operations we can do tell us that if we decrement this, we have to increment this. If we decrement this, we have to increment this. And so as we progress for each number, we check by how much we can increase this number such that it doesn't exceed x. Okay? And then we subtract that number from the number itself, because so that we give it as much of a chance as possible that it becomes smaller or equal to x. Okay? Yeah, I think this should be clear. The approach here should be clear. We can just go ahead and implement it. Yeah, let's do it. Okay, so let's implement the solution we just saw in the overview. So what we need is, first we need to define our binary search, right? So normal binary search, we said that our bounds are minus 1 and 10 to the power of 9 plus 1. So just outside of the boundaries of the range for the number. And then we do our normal binary search. We want to stop when low and high are just one distance apart. So low is at the last false and high is at the first true. And then we calculate our mid using just the normal, using binary method so that we avoid overflow. And we check if the number for mid is valid, right? We will call it can, you can call it f as well. Now, I'm going to pass a copy of the numbers array. You will see why in a second. And then if this is true, we want to maintain the invariant that high is always true, just the usual binary search. If it's false, we want to maintain the invariant that low is always false. And so we'll assign false to mid. And the answer is going to be high because high is the first true value. And that's exactly what we are looking for because that's the minimum possible value. And now we can just define our can function. So it gets an array and it gets the number, which is x, which is the one we want all numbers in the array to be smaller or equal to this x. Okay, so we'll just need the length of the array. And we said we will scan the array from left to right. You will see in a second why n minus 1. Now we check if the array value is bigger than x. That means even taking into account the previous element, it's not possible to make it smaller or equal to x, so we return false because that means our function cannot achieve the goal of can we make array, all a in array, smaller than or equal to x using any number of operations. Now we said that when we reach I, right, x minus array I is how much we can, is by how much we can decrement I plus 1, because this is by how much we can increment the element at position I without violating the condition of smaller or equal to x, right? So this is by how much we can increment array I without violating that array I needs to be smaller or equal to x. And so this is by how much we can decrement the array at position I plus 1. And so since it's by how much we can decrement it, let's just decrement it actually. And so let's call this maybe diff, and let's actually just take array I plus 1 and decrement it using that, okay? So that next time when we get here, we can just compare and see if it's smaller still or equal to x after doing this. That means it's possible to decrement it by that much, right? And get it to be smaller or equal to x, okay? And now at the end, if we do all of them, so now you see why we did n minus 1 here, because if we do leave n minus 1, this would be n, which is out of bounds. So we want this to not be out of bounds. That's why we stop here. Now at the end, the only thing we need to check is the last position, because we already checked all other positions using this. So we just need to check that the last position, which is n minus 1, is within the bounds. It's smaller or equal to x, because the other ones, since we reached it here, were all smaller than or equal to x. The only one remaining is the last one that we didn't iterate on here. And that's pretty much it, right? So if we run this and submit, it passes our test cases. Now, in terms of time complexity, binary search itself is of log of the range. Our range is 10 to the power of 9, so something around 30 potentially. So this is log of to the power of 9. Now, what is this function? This function just does one loop, so it does O of n here, okay? So this means the total time complexity is going to be this multiplied by this, right? And so total time complexity is going to be O of n log of 10 to the power of 9. And then the space complexity, we are not using any extra space here. We are doing these copies, so maybe O of n, but that's pretty much it. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you in the next one. Bye.